Have you ever just looked at something and wondered, what is really inside this? I mean, how do we know what our food, our medicine, or even the paint on our walls is actually made of? Well, today we're going to become chemical detectives and find out. Okay, let's start with a word we see all the time, pure. You see it on this jar of honey. Now, in everyday language, that probably just means, nothing's been added. But in the world of science, things get a whole lot more specific. And what about this bottle of water? The label says it's been remineralized. That means minerals were literally added back in, so it's definitely not just water. And right there, that's the exact point where our everyday idea of pure and the scientific one completely part ways. See, in chemistry, the definition is, well, it's incredibly strict. A pure substance has only one single thing in it, one element, like pure gold, or one compound, like pure sugar. Anything else, and I mean anything else, is an impurity, which makes it a mixture.
Okay, let's dive into our first case. Our first job as chemical detectives is to figure out if we're dealing with a single suspect, a pure substance, or a whole gang of them, a mixture. And believe it or not, our first tool is something super simple, a thermometer.
And here is the key difference, our first big clue. A pure substance has a sharp, fixed boiling point. Think about pure water, right? At sea level, it boils at exactly 100 degrees Celsius, not 101, not 99. A mixture, on the other hand, is all over the place. It boils over a whole range of temperatures. Just take a look at this. It's a mixture of ethanol and water. Pure ethanol boils at 78 degrees, pure water at 100. But as soon as you start mixing them, look what happens to the boiling point. It changes with every different combination. That drifting boiling point, it's a dead giveaway you're dealing with a mixture. Case closed on that one. Okay, so our boiling point test confirmed it. We have a mixture. Now for the fun part. We have to identify the individual culprits hiding inside. So how do we unmask them, especially when they're totally invisible? Just dissolved in a solution?
Well, we can actually run specific tests that trigger a chemical reaction. It's like we're forcing our invisible suspects out of hiding. They have to reveal themselves by forming a solid. This solid is called a precipitate, and its color acts like a totally unique chemical fingerprint.
And you know what? This fingerprinting method is wildly effective. As you can see here, if we just add a simple chemical, sodium hydroxide, to our mystery solution, different metal ions produce these amazing, uniquely colored solids. Copper gives you this pale blue, iron 2 gives you green, and so on. It's brilliant. And check this out. This is what it looks like for real. How cool is that? You can see that vibrant blue solid, which is the unmistakable fingerprint of copper ions. And that rust-colored stuff? That's screaming at us that iron 3 is in there. It's visual, it's immediate, it is fantastic detective work. All right, but what happens when the case gets more complex? What if our culprits aren't just one or two things, but a whole blend of different colored dyes all mixed together in a single drop of ink? We've got to find a way to separate them before we can identify them. This is where a really powerful technique called chromatography comes in. Honestly, the best way to think about it is like a race. The whole idea is to get all the different parts of a mixture moving, and because they all have slightly different properties, they're going to move at different speeds and literally separate themselves out. So, for the simplest kind, paper chromatography, it's basically a four-step deal. First, you spot your evidence onto some special paper. Then, you put that paper into a liquid called a solvent. The solvent travels up the paper and starts separating the mixture. And finally, you analyze the results. It's that simple. So first, we have to prepare our racetrack. We draw a starting line, in pencil of course, because pen ink would run and ruin the whole experiment, and then we carefully place a tiny spot of our mystery mixture right on that line. Next up, we put the paper into a beaker that has just a little bit of solvent at the bottom. The key is to make sure the solvent level is below our starting line. The paper then acts like a wick, just soaking that solvent up, and as it passes the starting line, it dissolves our ink spot and carries everything along for the ride. And this is where the magic really happens. Each different dye in that ink has a unique balance between how much it likes the solvent versus how much it sticks to the paper. The dyes that are really soluble and don't stick well, they're going to race ahead. The others will lag behind. And this difference in speed is what separates our original mixture into a beautiful series of distinct, pure spots. All right, so this is the crucial part, right? We've separated our evidence, we have these different colored spots on the paper. But how do we make a positive identification? How can we prove that this blue spot right here is, let's say, blue dye number 5, and not some other blue dye? What we need is a number, a unique identifier that's solid proof. And in chromatography, that number is called the RF value. It's a really simple measurement that basically tells us how far a substance traveled compared to how far the solvent traveled.
And the calculation? Oh, it's super simple. You just measure the distance the colored spot traveled from the starting line, and you divide that by the total distance the solvent traveled up the paper. That's it.
So for instance, if your solvent moved 10 centimeters up the paper and your dye spot only moved 5 centimeters, your RF value is just 0.5. And that little number, 0.5, that's not random. It's a physical constant for that dye in that solvent on that paper. It's like a fingerprint. It allows us to compare our mystery spot to a known substance and say with 100% confidence, we've got a match.
So, why does all of this chemical detective work actually matter? I mean, why should you care? Because understanding, separating, and precisely controlling mixtures is absolutely essential to creating pretty much every single product you use every day.
Well, it's because these carefully crafted mixtures, called formulations, are literally everywhere. They're not random at all. Every single ingredient is in there for a very specific reason and in a precise, measured amount to make the product work perfectly.
I mean, just think about it for a second. The paint on your walls, that's a formulation of pigments for color, a binder to make it stick, and a solvent to make it spreadable. The food you eat, your medicine, it's all formulations. And all this chemical analysis ensures that every can of paint and every jar of food is exactly what it claims to be.
So, from now on, when you see that word pure on a label, you'll know the real story behind it. And maybe you'll look at a can of paint or a tube of toothpaste and see it not just as some product, but as a masterpiece of chemical detective work. So, I have to ask, what mystery mixture are you now curious about?